During this stay-at-home season, you've likely become well acquainted with board games. But have you ever started playing and thought, hey, that looks like a 100-year-old problem? In 1859, Francis Guthrie conjectured that any map can be colored with only 4 colors so that no two same-colored regions share a boundary. Like in Blockus, where you lay down pieces so no 2 of one color ever touch, but not like Connect 4, where you line up same-colored tokens. Take this tangram 7-color puzzle. Look, we can color it in 6, in 5, and in 4. Corners are always fair game. Let's start with proving this is always possible for 6 colors. We can turn any map into a graph by turning each region into a vertex and each boundary into a connection. Wow, this looks like Chinese checkers. With maps, every graph is planar, meaning no 2 edges cross. Our question then is, can we color any planar graph in 6 colors? We're using a strategy called induction, which acts like dominoes. We prove that the first case is true, that the first domino will fall over, and then we prove the induction step, that each domino will cause the next to fall. Then we know that the first case implies the second implies the third, and so on, all the way up to infinity, proving the theorem for all cases. Here, our cases are the number of vertices, and we know the first case is true. We can obviously color 1 vertex in 6 colors or less. We can do it in 1. Now for the induction step. Here's an important statement in graph theory. Every planar graph has at least 1 vertex with 5 or less connections. We can model any graph with k vertices as protruding from this vertex. And for the induction step, we want to show that knowing this works for k minus 1 vertices also means it works for k. Here, if it works for k minus 1 vertices, we can color the graph without this vertex in 6 colors. Bringing that vertex back, we only need to color it a 6th unrepresented color. This completes our induction and proves the 6-color theorem. We can also prove the 5-color theorem. Our case of 1 vertex still works for 5 colors, so we only need to change our induction step to get rid of 1 more color. What if we change this red vertex to green? We would then need to change every green vertex connected to it to red, every red vertex connected to those to green, and so on. This process is always successful because we're simply alternating colors in a scheme that already works, unless we somehow cycle back to our main graph and turn our green vertex to red. But don't worry, we can always repeat the same scheme, changing this blue vertex to orange. Since we aren't allowed any edge crossings in a planar graph, this process could never cycle back to the orange and change it to blue. Thus, for any map, we've removed 1 color from around our central vertex, and we can color this a 5th unrepresented color. This proves the 5-color theorem. We sped through 6 and 5 colors, but it took supercomputers to prove the 4-color theorem. This was a landmark achievement with many scientific applications, including cartography, modeling economic growth, and transmitting radio frequencies. So next time you play what seems like a simple child's game, Blockus or Chinese checkers, you might be unlocking a mathematical secret with the power to transform the essential networks in our lives, from the neurons in our brains to the wide expanse of the internet.